Okay, guys, we are going to take a look at classifying chemical reactions. These are a bunch of different classes of reaction, and it's your job to know to be able to identify them. So I'm going to give you some characteristics. We're going to work through a couple to be able to come up with the full reaction and all of the information it is giving us. But there's a handful of reactions that you kind of need to be able to identify. The first two, A and B here, go together in a lot of ways, and you'll see why. So composition or a synthesis reaction, I think your book calls it composition. Synthesis reaction works as well. It's very simply, you're going to have more molecules or compounds turns into fewer molecules. This is organic chemistry in a nutshell. This is kind of how you would do the creation of a drug, for example. You're going to combine two types of things together to create some new compound out of it. So typically these things are made of carbon. So if you had two different compounds that you combined together, you would end up with a new compound that's kind of an amalgam of the two of them. So it's a kind of bound together, actually. So another way of looking at it is like that. And there's some kind of bond that's occurred between those two things. So we have created some new thing out of the two that we combine together. We have two molecules going to one. Typically, we're forming one molecule out of these things, but yeah, that's typically what it is. A decomposition is exactly as it sounds. You start with typically one compound and you go to more compounds. It decomposes into its component parts. So again, in this case, we are going from fewer compounds or fewer molecules to more molecules, RE molecules. I say molecules or compounds, they aren't mutually exclusive. Compounds is typically referring to ionic things. And anytime I say molecule, I'm referring to covalent. Okay, so a decomposition reaction, what we see in the demonstration here is I have solid sodium bicarbonate, and this is the actually part 2 of the reactions lab. And you're producing sodium carbonate as well as CO2 and water. So typically what you're going to see is one part of the more molecules is you're going to see the production of a gas molecule or water, okay, in its liquid state. Sometimes you see the formation of some kind of simple salt or a metal, a pure metal, something like that. Oh, that's a misspelling. Metal, there we go. Some kind of metal. So basically the ones that you really focus on, definitely gas, probably water. You kind of see those things form. Okay. All right, good. So those two go together. More molecules to fewer, your synthesis reaction, fewer molecules to more is going to be typically decomposition. Yeah, typically we start with one for decomposition and we end with one for synthesis. All right, next up. Here's where it gets a little bit interesting. This activity series that you see, the little chart below, you don't need to know that, but we're going to talk about it, and it's going to give you some idea of why things react the way they do. So here I have HCl combined with zinc. So what I will notice is I have some kind of aqueous compound. Okay, so this is H plus and Cl minus. We didn't really talk about acids. This is an acid. Very simply, this is an ionic compound. Although it does not, remember, ionic compounds, we're typically going to look for a metal, and we don't have it here. This is hydrogen. Hydrogen kind of counts. Again, it's kind of a crazy little thing. This is an acid. It acts kind of like an ionic compound. But what we do have, I should just say that this is aqueous. So some kind of aqueous compound, and then we have an element. Aqueous compound plus an element yields some other aqueous compound plus a new element. In fact, this is a new aqueous compound and a new element. Okay, so ultimately what you have is here's my zinc as a solid, and it goes together with the chlorine after. So here's my chlorine combined together with the zinc afterward. Here's my hydrogen, and here's my hydrogen afterward. So what you're going to notice is my hydrogen and zinc are going to switch spots. So hydrogen and zinc essentially switch spots on the other side. I've got zinc and I've got hydrogen. Okay, so zinc was the element on the left, and now it's aqueous on the right. Hydrogen was aqueous on the left, now it's aqueous on the right. Okay, so a positively charged substance replaces a positively charged substance. So we always switch partners. Yeah. So this is how we test and see if something is more reactive. If I react together something like, let's say, so if I have, let's say, lithium chloride, nope, let's not do that because that's not going to be great. Let's say magnesium chloride, aqueous, plus, let's say, potassium solid. I know potassium comes as a solid. There we go. So let's find out what we have here. We're going to look at the individual element on the left. This element right here, does potassium like to form a cation or an anion? Well, potassium is in group 1. This is going to form a cation. Which of the two on the right like to form cations, magnesium or chloride? Well, in fact, it already is a cation. Magnesium likes to form a cation. So when you identify the individual element, if it likes to form a cation or an anion, if it's a metal, it likes to be positive. If it's a non-metal, it likes to be negative. Then we know that this is going to replace magnesium, or so we hope. So when potassium and magnesium switch spots, I'm going to combine together K plus. I know potassium is going to react together with my chlorine, and my magnesium is going to be on its own. So when potassium and chlorine interact together, I just need one of each to make KCl, aqueous. Again, potassium was solid, now it's aqueous. Plus, now I'm going to have my magnesium as the element. Magnesium likes to be solid as an element. And that's it. So again, what we're going to notice is potassium, which was solid, is now in the ionic compound, and magnesium, which was aqueous, is now the element. So we're switching partners. You have one thing trading. We have to decide which. The activity series actually tells us which one is going to be more reactive. So you probably don't have to memorize this, but this is certainly interesting. The more reactive will be aqueous as a product. The more reactive will be the aqueous product. Okay, so more reactive means it's going to be aqueous product. Okay, the reaction will not happen. There will be no reaction if this is not true. Okay, so for example, platinum way down here is not reactive at all. So we always expect platinum to be in its elemental state on the product side of the reaction. Lithium is never going to be, it's hard to create lithium because lithium is so reactive, it always wants to be in the ion form. It always wants to be aqueous. Okay. All right. So we're going to do a handful of these, but single replacement, identify the element on the reactant side if it's cation or anion, and then decide. Because we do run into something like this where we actually have nonmetals in the other category. So again, we're going to take a look at the element here, fluorine gas. We know that fluorine likes to form anions. So that means that I want to talk about chlorine because chlorine likes to also form anions. Remember, anion is negatively charged. Cation is positively charged. I probably should have said that. Okay. So those two are going to switch spots. And that is exactly what we see. Chlorine is now the element, and fluorine is in the aqueous phase. Okay. Again, the more reactive is expected to be aqueous. Is fluorine more reactive? Yes, fluorine is more reactive than chlorine. So yes, we do expect it to happen. This reaction would in fact happen. Okay. But ultimately, you don't really need to know which one is more reactive. What you do need to know is anions replace anions if they're the element, cations replace the other cation if they're the element, and they just switch partners. It's a single replacement. Okay. Okay. Next up, a double replacement or a metathesis reaction. We did this one in lab, in the reactions lab, or you did see this one when you formed the yellow solid. Okay, so a double replacement, instead of a cation or an anion, a cation and an anion are going to exchange partners. So above in the single replacement, I decided if the element is a cation or an anion, and you have one exchange from the anion, the cation remains the same. For a double replacement, both are going to switch partners. So in this case here, I am mixing together the potassium iodine and the lead nitrate. And these things, when they combine together, okay, so think about it this way. I have potassium and I have iodine. Because they're dissolved in water, they're essentially just all over the place. There's no, they're not specifically going to stay together. They're just kind of everywhere. And in this one, I have lead 2 plus along with NO3 minus. Both of those have not yet been mixed. So there's kind of this division here. Okay. But as soon as I combine these together, now these things can pick new partners. So potassium and iodine are isolated because they haven't been mixed. Lead and nitrate are isolated because they haven't been mixed. And they happen to be aqueous when they're mixed. But as soon as I get rid of this, as soon as I mix them, now all 4 of these things are in solution together. What that means is potassium and iodine aren't the only pairs that can be created. I can now create a pair between potassium and nitrate because, again, this is negative or positive and this is negative. So we can have an interaction between the 2 of them, and we're going to create something. The lead can now interact with the iodide, and we can create a new compound out of that. So this, instead of these 2 being together, these 2 and these 2 are going to be together. So what we're going to do is we're going to take the ions and we're going to essentially just switch the partners, and we're going to come up with new compounds. Okay, so this is where ions are going to be super important. So again, if we focus on just this one, here's my potassium. Here's my iodine. And notice how the potassium and iodine switched partners, right? The potassium and iodine switched partners, as well as the nitrate and the lead switched partners. So we're creating compounds, out of all of these. Potassium and iodide, here's my potassium, here's my iodide. They've essentially split up. They've all gone into the party. They came to the party together. They left with a different partner. Okay, so that's kind of how these things happened. What we'll notice here is these are aqueous. This is aqueous. And this here is solid. So this lead iodide is known as a precipitate. It is a solid that forms, and we determine a precipitate based on the solubility chart. Turns out when lead and iodine find each other in solution, they start to solidify until you create this solid. Okay, so you create this ionic solid out of lead iodide. A precipitate forms because lead and iodine don't like to stay in water, but they do like to find each other. The preference is to join together and form a solid. Okay, so when you exchange things, you can have reactions happen, right? So they don't necessarily all stay in solution. In fact, if all stay in solution, nothing really happens. So they kind of form these solids. So these solubility guidelines. So here is a simple table. The first section of this is going to be our soluble ionic compounds. Okay, so soluble ionic compounds are on top. These soluble ionic compounds, I can't do it. All right, soluble ionic compounds are going to be on the top, and the insoluble ionic compounds are going to be on the bottom. So simply, any compound that contains any of these ions, I'm going to use blue because water, any compounds that contain those anions will be aqueous. They are in fact going to be soluble. There are a couple of exceptions. So if we look at this, if I have chloride combined with silver, okay, so chloride combined with silver, that is an exception. So if it is expected to be soluble, these exceptions are going to be solids, okay, so they're going to be insoluble. So that means that all of the exceptions are going to be solid. So what I mean by that is Ag with chloride, so AgCl. Mercury 2, which is kind of a special type of polyatomic that we're never going to talk about, forms a compound. You're never going to see that. Lead chloride forms a solid, okay? Any of these sulfates, what you're going to notice is most, almost lost that, there we go. Most of the sulfates are soluble, except strontium, barium, which are the heavy group 2s, lead and mercury. Okay, so you have these sulfates, which are kind of the exception here. Those form solids as well. So if you see this anion, you say, all right, perfect. Any nitrate, by the way, notice that any nitrate and acetate is immediately soluble. So any nitrate, acetate, hell, any of these ions here are expected to be aqueous. So if I have a chloride, I'm just going to check this list and say, oh, actually, it's not silver, mercury, or lead. Fantastic. It's going to follow the rules, so it's aqueous. Okay, so that's how we deal with this. These are soluble ionic compounds versus insoluble ionic compounds. So this is kind of the reverse. Anything with these is expected to be solid. So any sulfide, any carbonate, phosphate, or hydroxide is expected to be a solid unless it's in this list. And this list looks a little bit confusing, so let me just really sum up this list so we can make life simple. Anything soluble always. Again, soluble is going to be simply aqueous. Anything that contains NH4 plus, okay, so that would get rid of compounds that contain this. NH4, anything with NH ammonium is going to be aqueous. Anything with group 1 is also going to be soluble. So that gets rid of the alkali metal cations. And by the way, you notice that the list is kind of limited as soon as you get rid of those two. You're always going to get this chart, by the way. I'm not going to make you memorize this. But group 1 and ammonium are always going to be soluble. And then calcium, strontium, and barium, by the way, these are the heavy group 2s. Heavy group 2 hydroxide, heavy group 2, these are all going to be considered aqueous. So any exception is going to be aqueous. These, along with these, are aqueous. Okay, so one more time. Anything with this anion is expected to be aqueous. Here are the exceptions. Anything with these ions are expected to be solid unless it's in that list of exceptions. Okay. All right. So that's kind of the basics of a double replacement. Again, aqueous, these are aqueous versus solids. Okay. All right. So this group over here, solids, anyway. So that's kind of the idea. You will always get a solubility table. You don't have to memorize these things. So here we have the reaction of potassium iodide and lead nitrate. So we're going to take a look. We would call this thing the complete molecular equation. This is the complete molecular equation. So this is the hard part. What we're going to do is the next thing we're going to do is the complete ionic equation. Okay. When I do a complete ionic equation, anything aqueous will be an ion. Okay, so anything that's aqueous will get turned into its ion. So for example, this and this and this are all aqueous. So I'm going to rewrite everything, but I'm going to write what the ions are. I don't have to actually care about the number out front. I don't really care about coefficients. I do for the complete ionic. I want to make sure it's balanced, but for now I'm not. So I know Ki. Let's just look at Ki here, okay? Ki is broken into K and I. Both of those, by the way, everything's going to be aqueous unless I write something else, just because it's going to get really confusing if I have to keep writing aqueous. I know potassium is in group 1, so has a +1 charge. And I know iodine has a -1, so has a -1 charge. I have lead and I have nitrate. Lead is lead 2+, and I know nitrate, because it's a polyatomic, is always the same charge, NO3-. Again, I don't care about the number of nitrates, right? I've got 2 nitrates, I've got 2 potassiums, 2 iodides, but I don't really care about any of that. Okay, so I've got all of those aqueous ions. And let's do the products as well. I have K+ and I have NO3-. Good. Plus, this one right here is a solid, so I'm actually going to rewrite it. Okay, so my complete ionic equation is all of the aqueous things have been broken into their ions, and anything that is not aqueous, it just gets rewritten. Okay, so I have this entire part here, and then I have this, which is a solid, so I'm going to leave that alone. Okay, so this is the job of the complete ionic, is just to kind of put it out. K and I are no longer together. They're just going to be apart. Lead and nitrate are no longer going to be together. They're going to be apart. And we're going to take a look at these more complex versions of these. But now I'm going to ask you, now we're going to go through these ions one at a time, and we're going to ask, did it change? Is it still aqueous, or did it stay the same? So potassium is aqueous here. It is aqueous on the other side. So what we say is potassium could be eliminated from this because it's not interesting. It's actually not doing anything. It's aqueous on the left, it's aqueous on the right. We would call this thing a spectator ion. It's just watching the reaction. So I'm going to put K plus in the list of spectator ions. Next up, iodine. Iodine is aqueous on this side, okay? It is solid on the other side because iodine was here and now it's a part of this compound, this solid compound. So it's actually doing something. It's interesting. Let's keep it. Lead is aqueous here. It is part of the compound there. So we're going to hang on to it. We're not going to eliminate it because it's doing something. And then finally, nitrate is aqueous here. It's aqueous on the other side. We are also going to add the nitrate to our list of spectators. Nitrate's not doing anything special. It came to the party with lead in this case, and it left with no one. It's just kind of on its own. All right. So the spectator ions. So what I want to do next is I want to rewrite everything to write the net ionic equation. The net ionic equation is going to be everything that's left over. Just a quick aside, I am going to always write the positive one first. So although I have I minus, so I'm just going to, why don't I rewrite everything that I've got? Lead 2 plus, and now PbI2. I've already eliminated everything else. So those are all spectators, so they're not important. I don't have to write them out. The net ionic is always going to start with the positively charged one. And I'm going to add phase tags this time, plus iodine minus, which is also aqueous, yields lead iodide solid. Now I'm going to balance it. I have one lead here. I have one lead here. That's good. I have one iodine here. I've got two iodines there. So I'm going to toss a 2 in front. Okay, there we go. Job done. This is my net ionic equation. These are my spectators. That's what we're looking for. This is the interesting part of the reaction. When you mix together to create that lead iodide, right? What was happening was the lead and the iodine were finding each other and they were precipitating out of solution. By the way, you also might see something like this, a down arrow indicating that it precipitates out. But yeah, or here, you might see this. Okay. But this net ionic equation shows you the interesting part of what's actually going on. Complete the following reactions. Okay, so this one is, yeah, this one is not as interesting, or this one is actually quite a bit more difficult. So first of all, we are going to use our solubility tables here quite a bit. So we are going to come up with the phases a little bit later. But what I do want to do is actually, we can do it right now. What do I know about anything that contains a group 1? Anything with group 1 will automatically be aqueous. Okay, so group 1 is aqueous. So always look for group 1 and ammonium and recognize that if it has group 1 or ammonium, it's always going to be aqueous. What do I know about chlorides? Let's go back to chlorides. So what I know about chlorides is everything, it should be soluble. All the chlorides should be aqueous, except for silver, mercury, and lead. Silver, mercury, and lead should be solid. Otherwise, it's aqueous. I have barium chloride, so we would expect this to be aqueous as well. Okay, so this is how we start our molecular equation. We're going to balance this, but we've got to write out the other side. So we're going to have them switch partners, right? So what I'm going to do is the potassium and the carbonate are going to switch partners with the barium and the chloride. So we're going to have them switch, but let's just write out the ions because it's going to be easier that way. Because we're going to kind of create these things, again, the complete ionic, complete molecular, we're going to do complete ionic. So what ions do I have from these two things? So potassium and carbonate make up potassium carbonate. barium and chloride make up the second ion. So what I had was potassium was with carbonate, but now potassium could combine with either of these. Which one is it going to combine with? Well, positives like negatives, so barium and chloride. I'm sorry, potassium and chloride are going to combine on the other side. So if I make a compound out of potassium and chloride, so essentially another way of looking at it is, okay, these are the things that I now have in solution that can combine together. So potassium and carbonate, they were together. Barium and chloride were together. And now they're going to switch partners. And what compound do I make out of those? Well, potassium, let's say barium and carbonate would make, it's a 1-to-1, so I need one of each. So you should end up with BaCO3. Potassium and chloride should combine together to give me KCl. Right? Those are the things that I should end up with on the other side over here, because I'm going to have them switch partners, right? So let's write those out. So I'm going to end up with KCl plus, and we're going to leave a little room because we're going to need the phases, barium carbonate, because we're going to recombine. So what do I know about things with group 1? We know that anything with group 1 is going to be aqueous. What do I know about carbonates? So what do I know about the anion carbonate? Let's take a look. So carbonates, here they are, is expected to be solid. It was barium carbonate that we make. There are no exceptions. So any carbonate is going to be a solid. That means our barium carbonate is going to be a solid. Okay, I know these are long, but you're going to get better at them. So we could do a couple of things. So first thing I want to do is I want to balance, and this is the best way to do it. I want to balance this upper equation first. Yeah, let's do that. So I have 2 potassiums on this side. I only have 1 on this side, so I'm going to toss a 2 in front to balance them. 2 potassiums, 2 potassiums. I have 1 carbonate. I have 1 carbonate. I have 1 barium. I have 1 barium. I have 2 chlorides. I have 2 chlorides. This thing is balanced. That's what we're going to do for these. We're just going to kind of go back and forth with the ions that we have. Now, again, anything that is aqueous is going to get broken into its components. Anything that is solid just gets rewritten. So K plus Cl minus. Again, I don't care that I have 2 potassiums. I'm just going to write out the ions. And the final thing, we're going to eliminate anything that is potassium is aqueous here. It's aqueous over here. Potassium goes away. It gets listed as a spectator. Okay. Carbonate's a solid over here, so we're going to leave it alone. Barium's a solid over here. We're going to leave it alone. Chloride, aqueous on both sides. Chloride is the other spectator. Okay, so now I'm going to rewrite what I've got. Again, I'm going to write the positive one first. Barium 2 plus, which is aqueous, combined together with CO3 2 minus, which is also aqueous, yields barium carbonate solid. There it is. That is my net ionic equation. That is the result of those things, okay? We're going to do a bunch of these. We're going to try them out, but that's the idea, okay? All right, perfect. So you can try these. We're going to do these in class, but it's worth a look. In fact, I think I was probably supposed to do this down here. I got to look back at my own stuff. All right. Write the complete ionic. Again, more examples of writing complete ionic equations. Plenty of opportunities. By the way, we're going to be doing a bunch of these, so please get to know them. And the last thing, a combustion reaction for the section. A combustion reaction is when you take an organic, typically that contains carbon, hydrogen, oxygen, carbon, hydrogen, anything like that. You combine it together with oxygen. So some kind of carbon, hydrogen, oxygen compound, some type of molecular compound combined with oxygen to give us CO2 gas and water. CO2 and water gas. This is considered a combustion reaction. By the way, this releases a hell of a lot of heat, right? Any combustion reaction like the one we saw in lab, or you will see in lab, it's got a lot of heat, it's got a lot of energy that it releases. So breaking those bonds and forming those bonds, and we're not going to get into that much. So we get a combustion reaction. So there's two types of combustion. The very simple version of it is combining together, basically combining together with oxygen, a complete combustion reaction. And this is the only one you need to know, by the way. A proper combustion reaction is going to produce, just like above, CO2 plus water. We have to figure out how much of each of these is going to be done. So please balance this equation. All right, so go ahead and balance this equation. We're going to do this in class. That is a complete combustion reaction. Balance it. An incomplete combustion reaction is actually going to produce carbon monoxide as well as water. Okay, both of those gases, by the way, both of these are gases. So when you burn, this is actually propane, you're going to get carbon monoxide and water for incomplete combustion. The one that you really need to know is this one, though. When I say combustion reaction, I'm talking about this, but incomplete combustion, we'll talk about it in class. It's kind of a neat little thing. Okay, good. And then we're going to do reaction stoichiometry next week. That video will be coming sometime, hopefully before the weekend. All right, good. So balance this, give these a try, at least identify the phases of these, but we're going to walk through all of this in class. All right, good talk. See you all soon.